So without further ado, let's start the first talk. First talk is about collision-safe Equilibria with a virtual payoff from Aggelos and Aikaterini-Panagiota. The stage yours. Sure, hope I pronounce your name correctly.
Yes, it's very good. Thank you. Thank you very much for the introduction. So this is a joint work with Professor Aggelos Kiayias. And in this paper, we propose a framework for evaluating the incentives in blockchain protocols. And we use this framework in order to examine the incentives in the Bitcoin protocol and also in a protocol called Fruit Chain protocol, which was introduced by Rafael Paz and Lenzi. And let's start with the motivation for the framework. So why we introduced a novel framework. So the motivation was that many previous works used different frameworks in order to evaluate the incentives in Bitcoin, and they ended up in seemingly contradictory results regarding whether Bitcoin is incentive compatible or not. And it's nice to have a common framework that uses this framework to evaluate a blockchain protocol according to different utilities and also to evaluate different blockchain protocols. And our framework, compared to other works, takes into account simultaneously many important aspects of the blockchain protocols. So in more detail, our framework takes into account that the rewards of each participant are virtual, and so each participant may have a different view regarding its own rewards and also the rewards of each other participant. And this happened because the rewards are based on how many blocks have been produced by each participant and how many blocks exist in a local chain of a participant. So given that the participants may have different local chains, for this reason, they may have a different view on the rewards. And also, when we do a game theoretic analysis, we cannot assume that the protocol has some security properties because we are in a setting where the players are rational. So the same happens also with the utility. So the utility is also virtual, and in addition, our framework takes into account and includes a notion that is well defined for various types of utilities, not only the rewards, but also the profit, and is designed so that it is well defined when the utility gets negative values. And this can happen, for example, when the utility is the profit. Moreover, our framework takes into account that some coalitions may choose a strategy that is different from the protocol if they know that there is a small but non-negligible probability to increase their profit. So may have the case where some coalitions, even if they cannot increase their expected profit by deviating, they are risky, and if they can increase their profit with a very small probability but non-negligible, maybe they deviate. So our framework takes into account also this case. And let's see what an overview of what the framework includes. We firstly define formally the reward, the cost, and the utility functions. And after that, we describe an execution model with which we describe a finite execution of a blockchain protocol. And this execution model generalizes the execution model proposed by the Bitcoin backbone protocol, which is a paper written by Juan Garay et al. It is based also on the real world protocol execution model of Canetti. And finally, our framework includes a notion of Nash equilibrium that takes into account the previous considerations simultaneously and also generalizes the notion that is proposed in the protocol called fruit chains, which is written by Raphael Paz and Elaine C. So first I will give an overview of the framework before I give our results. So let's see the execution model briefly. We have N parties, and all the parties take input from an entity called environment. This entity represents all the external world to the protocol, and we have that in the beginning of the execution, an entity called adversary corrupts a set of parties, and this set will be called, denoted by T. And so the execution is progressing in rounds, and during each round, the protocol, the parties that are not corrupted, follow the instructions of the protocol, and they ask some oracles a specific number of questions, of queries, and for every query, they incur a cost. So these oracles represent some cryptographic task. For example, an oracle can be a random oracle in the case of a proof of work blockchain protocol, or for example, an oracle can be signing a block in case of a proof of stake protocol, or verifying transactions or other cryptographic tasks. And at the end, when each party has played during the round, at the end, the adversary is activated and can deviate arbitrarily, so it's not restricted to follow the protocol. He can deviate arbitrarily, but he is restricted to how many queries he can ask the oracles. For example, it can ask at most a specific number of queries each oracle. The communication between the parties is determined by functionality that was defined in the Bitcoin backbone protocol, which is called diffuse functionality. And this functionality gives an advantage to the adversary because it gives to the adversary the opportunity to delay the messages by the uncorrupted parties until the end of the round. So the model is synchronous because the adversary can delay the messages, but at most until the end of the round. So this is a brief description of the execution of an arbitrary blockchain protocol. And now let's see what our framework does. So for every environment, for every possible environment, the framework examines the utility of the adversary in two types of executions. In the first type of execution, the adversary, when it is activated, follows the protocol, except the fact that it uses its network advantage. So when we say that it uses its network advantage, we mean that it delays the messages coming from the honest party and gives its blocks and its solution first. And the second type of execution, it is an execution where the adversary can deviate arbitrarily. So our model is strict in the following sense. When we examine the execution where the adversary follows the protocol, we use the minimum utility among the views of the honest players, because if you recall, all the honest players have different view. So when the adversary follows the protocol, we use the minimum utility among all these views. But when in the execution where the adversary deviates arbitrarily, we use the maximum utility that it can have among the views of the honest players. So we have the adversary have a dilemma to follow the protocol or to deviate. And if it holds this inequality with overwhelming probability in the security parameter, we consider that the adversary will follow the protocol. So this inequality says that the adversary cannot increase very much its utility by deviating, and this happens with overwhelming probability. And you can see here that we have a multiplicative a factor here, epsilon, and an additive factor here, epsilon prime. We use here absolute because the utility can be negative. And here, if you recall, we have used the max utility and here the mean utility. So if the adversary can convince just one honest party that its utility is much higher with non-negligible probability, then we assume that the adversary will deviate. And if for example, our protocol satisfies this inequality, this means that our protocol is G epsilon prime coalition safe equilibrium with virtual payoff. And here, T is an upper bound on the number of the parties the adversary can corrupt, and epsilon and epsilon prime are the multiplicative and the additive factor we have seen in on the previous slide. So we have this notion of equilibrium, and using this notion and this framework, we used the following utility functions in order to evaluate the Bitcoin protocol and the fruit chain protocol. So the utility functions that we used were absolute rewards, the first one, the second absolute rewards minus absolute cost, and the third one was relative rewards. So initially, in our results for the Bitcoin, we take into account only the cost of mining, so which is the cost that the participants have in order to ask the random oracle some queries. So let's see an overview of the results in the Bitcoin protocol. So let n be the number of the players and what our results say is the following. So we have the positive results for the Bitcoin protocol, and our notion is satisfied in the following cases. The first case is when the utility is absolute rewards minus absolute cost. The cost of mining is small compared to the rewards of each block, and also the block difficulty is fixed. And this happens, our notion is satisfied for coalitions up to n-1. So here, n-1 refers to T here. This is the upper bound of the number of the parts the adversary can corrupt. So in addition, we generalized more our results, and we found that our notion is satisfied also in the case where the block difficulty changes, but changes after a fixed number of rounds. And this number of rounds depends on, is proportional to the security parameter. So if the difficulty changes, but changes in this way, then we can have also a positive result for Bitcoin. Let's see now the negative results for Bitcoin. So it's not satisfied for small epsilon plus epsilon prime, which means that the adversary can deviate and increase its utility by doing a strategy different from the protocol. So in the following cases, the first case is that the utility is absolute rewards minus absolute cost, but now the block difficulty changes after a number of rounds that depends on the number of blocks in the chain. So for example, after 2016 blocks are produced, which is the rule that now Bitcoin has. So if we use this rule, then our notion is not satisfied. And just to give an intuition why this happens, we have a strategy that is performing selfish mining until the the difficulty changes, and after that the adversary mines follows the protocol. So initially it performs selfish mining in order to decrease the difficulty of blocks, and so that it has the opportunity to produce more blocks in the next period. And also, for the same reason, due to selfish mining, we prove that our notion is not satisfied when the utility is based on relative rewards. So again, for the same reason, because of a strategy that it is very near to selfish mining. So we also used our framework in order to evaluate decentralization in Bitcoin. So we found that if we take into account also the cost of verifying the transactions, so if verifying the transaction is not zero cost, then we have an equilibrium that is centralized. And this strategy profile is that all miners form just a single dictatorial pool, and in this pool, the pool leader verifies the transactions, so ask transaction verification oracle, and it gives the proof of work instances to the other members, and the other members perform mining, and when the party finds a block, it shares this block. And the way the rewards are shared is the following. The pool leader will hold an amount that is equal to the cost it incurred because of verifying the transactions, and the remaining amount is shared proportionally to the proof of work instances. So this is an MVP, and it's for coalition of up to n-1 participant. And the intuition why this is an MVP is that miners have the incentives to share the transaction verification costs. So if they alone, either they mine alone or they mine in a secret pool, in expectation they will have the same rewards, but when they mine in a single pool, then they share the verification costs. So for this reason, we have proved that mining in a single dictatorial pool is an MVP. And now let's see an overview of our results regarding the fruit chain protocol. So we have proved that our notion is satisfied when we have utility profit, absolute rewards minus absolute cost, and coalitions up to n-1. And we have also shown that our notion is satisfied when the utility is based on relative rewards and coalitions here are smaller than half n. Just to note that the fruit chain protocol assumes fixed target, but it's an interesting research direction to search what happens if the fruit chain protocol had the difficulty to change, because our intuition is that even if the difficulty changes as in Bitcoin, when we use a utility absolute rewards minus absolute cost, then we can have a positive result, which will be different from the Bitcoin.
Sorry, Aikaterini, you have only 1 minute to maybe you can consider wrap up.
Great. Okay. So yes, I have one more slide. Thanks for the reminder.
Great. Thanks. Sorry for the interruption.
Great. So this is an overview of regarding the license fruit chain protocol. And the last thing that our paper includes is that we define a property called weak fairness, which is weaker than the fairness, the notion of fairness proposed in the fruit chain protocol and other previous works. And this property is sufficient for a protocol in order to satisfy our notion MVP when the utility is based on relative rewards. So if a protocol satisfies this property, then we know that this protocol is MVP when the utility is based on relative rewards. So this is an overview of our results. Thank you very much, and I'm waiting your questions.
Yeah, thanks.
Let's stop sharing also.
Yeah, very nice talk. And maybe we can have a very short question. And we have one question. Okay, so there's a question in the post, and it seems like the question already being answered. So the question is difference with the model with fruit chain. Is there any other, if you have any other question, maybe we can consider one more. Just type in the chat.
Maybe I add something more to this. May I add something more to regarding this question? Yes. So here, first of all, one difference in the model is that we have both multiplicative and additive factor, and we have also, in addition, we take into account that the views of the participants may be different, and our framework is well defined. Even we don't assume a common prefix property. So our model is well defined, and we don't need to assume a security property for the protocol in order for definition to be well defined. And also regarding the results, the improvement compared to the fruit chains protocol is that we prove that when we have utility absolute rewards minus absolute cost, then we can have collisions up to n-1, not half n. So this is the first improvement, and we also proved formally this one for the utility relative rewards. So this is a quick overview, and we have in the paper also a detailed answer how the models are comparing.
So for the sake of time, there's actually another interesting question from Itai, and probably Aikaterini, you can see in the chat. For the sake of time, probably you two can talk more offline. And let's probably move to the next talk.